네, 여러분 안녕하세요. 물리화학 수업을 시작하도록 하겠습니다. 지난 시간에 이어서 이번 시간에도 엔트로피와 관련된 연력합체 2법칙에 대해서 말씀을 계속 드리도록 하겠습니다. 결국 내부 에너지와 엔탈피는 시스템 내에 열 에너지가 얼마나 출입이 됐느냐 하는 것에 대해서 이제 초점을 맞췄다고 하면은 이 엔트로피 같은 경우에는 그러한 그 변화가 어떠한 방향으로 흘러가는가, 그리고 어떠한 그 열 에너지에 의해서 그 시스템의 상태의 변화가 어떤 식으로 되는가 하는 거에서 좀 초점을 맞춘 겁니다. 이게 그래서 자발적으로 발생하는 반응인가. 그러니까 자발적, 비자발적이라는 말이 뭐냐면 결국은 이게 그냥 가만히 뒀을 때 이게 그냥 일어나는 반응인가, 일어나는 어떠한 그 현상인가, 아니면 그렇지 않고, 그냥 가만뒀을 때, 그, 어, 그러니까 어떠한 그 시스템에서 이게 우리가 어떠한 특별하게 반대적인 에너지를 공급하지 않는 상태에서 우리가 지금 보고 있는 이 반응이 과연 이게 저절로 일어나는 반응인가, 아니면 어떠한 좀 특수한 반응인가를 판단할 수 있는 척도를 매게 해주는 게 바로 이 엔트로피고요. 그리고 그 엔트로피에 대해서 지난 시간에 계속 설명을 좀 드렸었습니다. 그래서 계속해서 그 엔트로피의 그 특징에 대해서 좀 설명을 드리는 거고요. 여러 가지 그 엔트로피에 관련된 어떠한 그 이론들, 그리고 그런 것들에서 설명을 드리고 있는 건데, 여러분이 이제 사실 여기서 여러분이 주요하게 이제 이해를 하시면 되는 건 과연 엔트로피가 뭐고, 엔트로피 정의가 어떻게 되고, 그래서 그 엔트로피를 이용해서 우리가 어떤 것들을 좀 확인할 수 있는지 정도만 여러분이 사실 아시면 돼요. 그렇게 좀 생각을 하시면 되고요. 네, 그래서 한번 같이 이야기를 한번 오늘 수업을 계속해서 좀 이야기를 나누도록 하겠습니다. Okay, so hello everyone. So until the previous classes, we have discussed about the definition of entropy and also some kind of fundamental concept which is related to this entropy concept, entropy system. So today we will talk about a little bit more about the entropy system. So first, there is the thermodynamic temperature. So this is kind of one of the concept which is related to this the, the, the the entropy system. So what is the thermodynamic temperature? The thermodynamic temperature scale could be defined in terms of the efficiency of a heat engine. So like this. So it can be, this is the efficiency, and this is the temperature of the hot source. So the thermodynamic temperature can be defined like this. T equal 1 minus efficiency and TH. So the person Kelvin, he make this kind of Kelvin scale, which is the special case of thermodynamic temperature scale. And this is defined by using the water at its triple point as the notional hot source and defining that the temperature as 200 the 73 Kelvin exactly, which is the 0 degrees C. So what this means is at this point there could be some kind of this is a kind of a critical temperature for the change of status of water, and this could be also can be calculated by this kind of thermodynamic temperature scale. right? So this is a kind of one of the relation between this efficiency of this the temperature. So as we know, this efficiency can be written as the minus Tc, and therefore Th over Tc equal 1 minus efficiency. So therefore Tc equal 1 minus Th. So if we know this kind of efficiency, then also we have some temperature for this heating source, then we can calculate this temperature for this cold sink. And this Kelvin scale is the use this 273 Kelvin for this pH. And by using that temperature, they can calculate the kind of TC or some efficiency for a system using this water. So this can be a Kelvin scale, right? So how can I say? So this is kind of the some definition. So we know this kind of the thermodynamic temperature. So if we rearrange this definition of efficiency about the kind of temperature terms, then we call this thing as a thermodynamic temperature. And Kelvin used this the equation for a special case of a thermodynamic temperature scale. So how can I say? So there is a thermodynamic temperature, and this is the area of thermodynamic temperature, and Kelvin scale is the part of this thermodynamic temperature. So this will be easier for your understanding. So Kelvin used this the TH as water temperature of TH equal to 176 K for water. And if the system using this kind of temperature for this thermodynamic scale, then this is called as Kelvin scale. Okay, so this is kind of some kind of special definition, so you don't need to so worry about that. You cannot understand fully about this system because this is kind of just definition. And there are still discussion about this kind of definition too. So I just want to give you some. There are also this kind of scales for explain about some kind of system. So yeah, so this is also one example. And also the one of the last things, it's not the last, I mean, this is the last concept we will talk about through this first part of this the entropy system. So there is the Clausius inequality, right? So the Clausius inequality is the more work is done when a change is reversible than when it is irreversible, right? So this is one of the kind of how can I say, this entropy system is kind of a scale to evaluate the kind of a system, whether it is the the spontaneous or non-spontaneous. So that's why they make them kind of equation. And then if the kind of system is consistent with it satisfied some kind of equation, then we can say that system is the spontaneous or not. So the thermodynamic temperature is one of the kind of definition system. And there are also Clausius inequality. So we will also talk about this Clausius inequality. And the finally, this is the Clausius inequality. So if some reaction is satisfied this Clausius inequality, then we call that the system is spontaneous. The change is spontaneous. So how can we derive this Clausius inequality? First, we will start with this concept. So there is the reversible and irreversible change. Then this work for this reversible change will be bigger than this irreversible change. Yeah, right? Yeah, because this the irreversible change is the spending some kind of energy for some heat. So that's why no the 100% of energy can be done for this work, but the reversible is the kind of uh, the go and forth, back and forth, the change of a system. So that's why this work, the scale of amount of work should be larger for this reversible change than the irreversible change. So that's why we can say this thing as like this. So dW reversible is larger than dW, right? And if the energy leaves the system at work, then the reversible, the amount of reversible will be minus, right? The signal is minus. And then this is also minus, right? So that's why we can simply rearrange this thing as the dW minus dW reversible, which are larger than 0. And by the way, this internal energy is a state function, right? So therefore, regardless of the process is the spontaneous or not, I mean reversible or irreversible, the amount of internal energy change should be same because it's a state function. So that things can be written as d mu equal dq plus dw equal dq reversible plus dw reversible. Right? So then we can rearrange this equation as the like this here, and this is here. Then we have dq reversible minus dq equal dw minus dw reversible. Right. And because this is the bigger than 0, so that's why we can simply rearrange these things as the so that's why dq ref dq equal also 0, right? So that's why dq ref and dq, right? So if we just divide this the temperature for this both side. Then we have well, right? And what is it? This is the ds in terms of definition of entropy. So therefore, we can finally have entropy is the dq, and this system is called as the Clausius inequality. So what this means, so if there is some kind of reversible change in a system, then the change of entropy should be always the positive. I mean, there it is not possible for the entropy to be decreased in the system. So that's the meaning of this Clausius inequality, right? And also this Clausius inequality also means the spontaneous changes should be always this irreversible. Right? Because the, how can I say, the total entropy, the total entropy will be ds plus ds surrounding, right? And this should be bigger than 0. Right? So this kind of this, how can I say, the meaning of this entropy is the bigger than 0, then that system is the change it to spontaneously to be a random motion. And this kind of situation is the irreversible process, right? So that's why, in terms of this cluster inequality, the right means the this kind of entropy change is always bigger than 0. So therefore, depending on this cluster inequality, the system, if the how can I say, the spontaneous change of the system should be reversible, so not the reversible. Okay, so we can also use that kind of Clausius inequality for this kind of system. So let's see if there is some kind of hot source and there's a cold sink, and heat is a transfer from this hot source to this cold sink. Then ds, the entropy change at this hot source, will be th dqh, right? And the entropy change of this cold sink will be ds equal tc and dqc, right? And since this is kind of the energy releasing process, so that's why is a QH is the minus dq. So that's why you can say that th over minus dq, and this is the th over plus dq, right? So we can say, because this is the spontaneous reaction from this hot source to this the cold sink, so that's why this should be how can I say no? So that's why the in terms of Clausius inequality, the th we can say that this is the QH, and also for this cold sink, we can also say that yes equal the QC, right? So for this, so therefore the ds total for this system will be th over dqh plus tc over dqc, right? However, the dqh is the same amount of dqc, but only the signal is t minus. We can say that as this value to here, so therefore ds total minus th dqc plus tc dqc, and this is the tc minus 1 th over 1 dqc, right? And because the how can I say, tc equal smaller than th, so that's why this will be bigger than 0, right? And the qc is also plus because it's the absorbing heat, so that's why this is also plus. So that's why this is larger than 0. So that's why this is the that means ds equal 0, and this is the spontaneous system, the reaction. Okay, so that's why if we just link this kind of hot source with a cold sink, and the spontaneous change of the system is the heat transfer from this hot source to this cold sink. So that kind of process is spontaneous. I mean, actually, this is a kind of common sense, right? So you will instinctively know that if we connect this kind of a hot source with this cold source, then the heat will be transferred from this hot source to this cold sink. And but in here we are expressing the kind of change. I mean, the kind of a spontaneous change, which in your mind is just kind of common sense with this kind of thermodynamic theory, especially using this entropy system. So yeah, so yeah, so this is the kind of the way to explain the kind of the situation about this thermodynamic laws. And the one more thing is that if this that kind of system is an isolated system, then there could be no heat transfer, right? So in that kind of isolated system, the entropy cannot decrease when a spontaneous change occurs, right? So in that case, the ds will be 0. So anyway, if ds is also 0, then still this is the satisfying this the concept of mm, the entropy. Okay, so the now we learned about some kind of the fundamental theory or some fundamental concept of this entropy system. So this is a kind of a quick summary for the things. So now you know this. This is the definition of entropy for this thermodynamic system. So you can simply define this entropy like this. And we can also calculate this the entropy change for this surrounding, which is the similar way, same way as the entropy change of the system. And we also talked about there is some kind of Boltzmann formula for this entropy system. So this can be used for some the configuration system of the number of molecules, or some the electron configuration for some kind of atoms. So that kind of things can be uh, evaluated by using this Boltzmann formula. And this is also called as the some statistical the thermodynamic system. And also we have learned about this the efficiency of Carnot cycles. So during this Carnot cycle, we also define this thermodynamic temperature scale. And also we are having that this the final concept for entropy, which is the Clausius inequality. So the concept with this Clausius inequality is the process have irreversible change, then entropy should be decreased, should be increased, right? And all the kind of spontaneous changing should be reversible, depending on the Clausius inequality, right? So if we can simply calculate this T over dq, then we can evaluate the kind of a change will be irreversible or not, or if that is irreversible, then it should be bigger than zero. And that kind of a system also will be spontaneous changing. So actually, this is the so all things actually we have learned. So even though we discuss about some kind of the way to prove that kind of equation or definition, but the most important thing you have to understand about this formulas, not the kind of process to define the system, but we have to some know about this physical meaning of this equation. And then, and next you have to memory about this kind of equation. So if somebody say, what is this kind of cross inequality, then you can respond that this is a class inequality. And this class, and the depending on this class inequality, we can say that spontaneous change is a reversible process. Okay, so let's continue for more about this entropy change accompanying specific process. So this is the kind of the way to explain about some kind of specific process using this entropy system, right? So it's not so difficult. So you can just, this is just kind of a list of examples. So how can we use this entropy system for some specific situation? So you can just see there could be the kind of way to use the entropy system for some specific process. Okay, so the key point for these things is first, the entropy over perfect gases increases when it expands isothermally. So we'll talk about this thing. And second, the change in entropy of a substance accompanying a change of a state at its transient temperature is calculated from its enthalpy of transition. So what this means, so as you know, so entropy is the Ts is called dq rev. But in this kind of a transition system, the Q rev is the enthalpy change at the transition. So you can say Ts equal T over Th. So such things we will also talk about things. And then the third thing is the increase in entropy when a substance is heated is expressed in terms of heat capacity, right? The Cv and Cp. So we can express the kind of heat capacity for the entropy change during this heating system. And finally, the last thing is the entropy of a substance at a given temperature is determined from the measurement of its heat capacity from T0 up to the temperature of interest, allowing for the transition in that range. So the measuring the entropy is how can I say? The way to measure this entropy is just measuring this heat capacity and then find the point of a phase transition. And using that kind of phase transition and the heat capacity, we can calculate this entropy system. Okay, so this kind of things we will briefly discuss about in this chapter. So let's talk about this thing. So first, the expansion. The entropy change for the isothermal expansion of a perfect gases can be written as the delta S equal nRLV1 over VF, right? So this is the we already solved together, right? Here. Yeah, here. See, we already solved together, so I will not discuss further about this thing here again. Right, so the total change in entropy can be expressed as like this. So because the energy transfer to the surrounding will be same as the energy transfer to system, but it's negative. And this is a QREF with nRT ln V1 Vi over Vf, and then delta S surrounding is the T surrounding, and this is the minus T QREF, and this is the minus nR ln V1 Vi over Vf. So this changes. So this is kind of a specification. This is the isotomal expansion of perfect gases. So it satisfies this PV equal nRT. And this is isotomal expansion, which is the temperature is the constant. So this change is the negative of the change in the system. So we can conclude that this the delta total as total is zero because there's only minus, which is what we should expect for reversible process. So what it means is isotomal expansion of perfect gases is the reversible process. Right? But what about this pre-isotomal expansion work? So if there are no boundary and this is if that is a irreversible process, then delta S surrounding will be zero, right? Because there is no temperature or no heat energy the transfer to the surrounding. And this is zero. So that's why the can I say the how can I say the yeah, so I hope to say that this, so what is the pre-isotomal expansion work? So this is kind of the expansion at the vacuum system. Then P will be zero. Then therefore, there could be no work, which is the W equal zero. And because this is the expansion also isotomal because the T is equal zero, so that's why delta mu equal zero. So then delta mu equal Q plus W, and this W equal zero, and this is zero. So that's why the Q is equal also zero. So delta S equal surrounding is T surrounding over Q surrounding. So that's why this is also zero, right? So in that case, we can simply say that the total entropy system is just like this. Like this. And because this is the reversible process, this should be larger than 0. Right? Okay, so now we will talk about this phase transition. So in terms of a phase transition, the entropy of phase transition is the same as the energy transfer at this system, because there are no, how can I say, uh, the 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 process of the phase transition, it is a constant pressure. So that's why we can say this Q equal delta H transition. So we can say this entropy change of transition is T transition over Q transition. Then this is the delta H. So we can say that this is delta transition S equal T transition over delta H transition. Yeah, so we can say like this. So this is one of also example for this entropy system for some specific case. And what about this heating system? So let's calculate this entropy during this heating. So the case is like this. The entropy of a system at a temperature Tf could be calculated from a knowledge of its entropy at another temperature of Ti by using this kind of system, right? Because the S equal T dq ref, and if there is some kind of temperature change from T1, Ti to Tf, then we have delta S equal I F T dq ref, right? Okay, so the how can I say, the total entropy at this temperature Tf should be sum of its initial entropy and plus the change of entropy, this one, right? And in our previous classes, we have learned this at the constant pressure, the Qref is equal to this Cp dt, right? So you can simply replace this dqref with this Cp dt, like here, like this. Then we have this final equation. So if we use this constant volume, then we can use it Cv instead of this Cp. Okay, so when the Cp is independent of a temperature, so then we can simply pull out the Cp from here. Then we have this Sti plus Cp integral Titf dt over dt. Right, then this one is the Cp ln Ti over Tf. So finally we have Sti plus Cp ln Ti over Tf. So this is how can we calculate this entropy during this heating system. Okay, so let's solve an example for this kind of a specific case. So they calculate this entropy change. So let's calculate this entropy change when argon at 25 degrees C and under 1 bar of pressure in a container of a volume of 0.5 decimeter 3 is allowed to expand to 1 decimeter first, and it's simultaneously heated to 100 degrees C. And if for perfect gases CVM equal 2 over 3R, then let's calculate this entropy change. So I'll give you a few minutes, and then please calculate together for this system. Okay, so let's solve together. So what is the hint for this example? First, this is the perfect gas. And the first, how can I say, the first process at this, the expansion at this 25 degrees C, at this 1 bar. So this is the 1 bar from this 0.5 to this 1.0. So we will see this process first. This is the same temperature, constant temperature, and constant pressure. So because this is constant temperature, so this is the isothermal expansion, right? So for this isothermal expansion of the perfect gases, the entropy change can be calculated by this delta S equal nR and ln Vi over Vf, right? So we learn these things from our first part. And the entropy change in the second step, this step, the temperature is changed from this 25 to this 100 degrees C. So let's calculate this one. So in this kind of the changing of temperature, we can calculate, we can use this equation, this one, right? So we can simply NCV ln Ti over Tf, right? So we are expressing this because this is the constant volume at here in the second step. There are no volume change, but the volume is the constant as 1 bar. 1 decimeter. And then CVM for perfect gas is the 2 over 3R. So we can simply put this one here. Then this is the 2 over 3 NR ln TI over TF. Right? So we just put this one here. Then we finally have NR ln TI over TF 2 over 3. And the overall entropy change of the system is the sum of these two changes, because this is the, like this, the STI, right? And this is the change of delta S from this TI to T2, TF, TI from TI to TF. We can simply add these two things. This is the NR ln VI over VF, and this is the NR ln TI over TF 2 over 3. And using this kind of mathematical equation, we can rearrange these terms as the NR ln VI over VF multiply with this TI over TF 2 over 3, right? And because this because this is a perfect gases, and for the perfect gases, the PV equal nRT will be satisfied. So that's why N equal PI VI RTI, right? So we will put this thing here. Then R will be removed, and finally we have TI over PI VI and ln VI over VF and TI over TF 2 over 3. And just simply put this all this value in here, then we can calculate this delta S value. Right? This is the about 0.173 joule per Kelvin. Right? So this is kind of the summarizing examples for this specific case. First, we know this for the isothermal expansion, the delta S. We have to remember this three things. Delta S is NR ln VI over VF, right? And in the heating system, then STF equal STI plus C ln TF over TI. C can be Cp at this constant pressure, or C can be Cv at this constant volume. So these two things will learn. And the other thing is the delta at this transition of phase transition situation. The change of entropy during this phase transition is the TTR transition temperature over enthalpy change during this transition. So that is the entropy change. So these three things is the main concept for this entropy change. Okay, so yeah, so this is also one of the examples. So how can I say? You don't need to consider. I mean, I will not talk about these things. So there is only the how can you measure this entropy? So I just will give you explanation um, by my work. So we can simply calculate this kind of the heat capacity depending on the temperature, and there could be this kind of a transition. And at this transition, we can use this kind of divide extrapolation, which is this kind of relation. And by using these things, we can calculate this entropy change at this system. So this is the one of the example to how can we measure this entropy change. So the concept of this thing is there could be some the transition of the system, then we can simply calculate this entropy change at this transition point. But that's the point of this entropy measurement. Okay, so yeah, so before go further, would like to give you a quick summary in Korean, and then stop this chapter or stop this class here. Then we go further for this entropy system. 네, 그래서 저희가 오늘 배운 게 여러 가지 개념이 있습니다. 그러니까 지금 새로운 개념들이 여러분에게 이제 지금 막 이렇게 여러 가지가 나오고 있는데, 어쨌든 핵심은 이제 사실 여러분이 이제 기억하셔야 될 게, 사실 뭐 여러 가지 이제 뭐 증명 단계라든가 이런 것들을 여러분이 완벽하게 이해를 하신다면 이런 여러분 지금 배우고 있는 텀에 대해서 훨씬 더 기억하기 쉬우실 거예요. 그렇지만 이제 뭐 이 과목 내에서 이제 그거를 모두 여러분이 다 할 수 있어야 된다. 뭐 이런 거를 뭐 여러분이 다 해야 된다. 뭐 그런 의미는 아니고요. 사실 과목에서 여러분이 기억해야 될 거는 요거와 이거의 의미만 아시면 되는 거예요. 이런 거는 이제 수업 내에서 이제 다루는 그런 내용이고, 실제로 여러분이 아셔야 될 거는 뭐 이런 거의 의미들, 이런 걸 아셔야 되는 거고. 그래서 첫 번째로 배운 게 우리가 thermodynamic temperature라는 걸 배웠죠. 그러니까 원래 efficiency라는 거를 우리가 이제 이전 시간에 배웠었고, 이 efficiency 기본으로 해서 이런 식으로 이 temperature 기준으로 이 식을 다시 정리해 준 거를 이제 thermodynamic temperature라고 부르고 있고요. 그 중에서 어떠한 그냥 스페시픽한 케이스, 그러니까 이 TH가 물의 어떠한 트리플 포인트인 273도 켈빈, 273도 켈빈을 핫소스의 템퍼러처라고 두고 계산한 이 TC와 이런 이피션시를 켈빈 스케일이라고, 뭐 특별히 이제 그 구간대에서 그렇게 계산한 걸 켈빈 스케일이라고 얘기한다. 이렇게 이해를 하시면 될 것 같아요. 결국은 이제 요 켈빈 스케일도 이제 요거의 일환인 거죠. 그래서 요것만 아시면 되는 거고. 그 중에서 이제 클라우시스 이니퀄리티라는 게 있는데, 뭐 이렇게 여러분한테 이제 이건 쭉 다 설명을 드렸고요. 결국 클라우시스 이니퀄리티라는 게 이제 이런 식으로 표현이 되고요. 그러니까 이 DQ, 그러니까 이 리버서블한 프로세스에 대한 엔트로피 값, 그러니까 이 엔트로피의 변화가 요 T분의 이 DQ 값, 그러니까 히트 에너지가 트랜스퍼 됐을 때보다 이게 크다. 이게 이제 클라우시스 이니퀄리티인데, 요거 이제 사실 이제 요 포인트는 요 클라우시스 이니퀄리티 요것도 있지만, 결국은 이거를 이렇게 쭉 계산해 보면 요 식이 의미하는 거는, 이 식이 결국 의미하는 거는 이 그, 이 비자발적인 그 어떠한 그 변화가 일어날 때 이 엔트로피의 체인지는 항상 증가를 한다. 그러니까 어떠한 이제 변화가 이제 계에서 우리가 어떠한 그 자발적 변화가 이제 일어날 때에는 자발적 변화가 일어날 때에는 그, 그 엔트로피가 항상 증가하는 방향으로 이제 간다. 그러니까 비자발적인 방향으로 이제 변화할 때에는. 그러니까 어떤 시스템이 변할 때는 엔트로피는 증가한다. 그러니까 결국 이 무질서하다는 의미잖아요. 그렇게 쉽게 이해하면 돼요. 이 엔트로피는 증가하는 방향으로 가게 된다. 네. 그래서 특히나 이게 그 리버서블 프로세스에서는 요 DQ, 이 DS 토탈이 결국은 이제 0이 될 텐데, 결국은 0이 된다는 거는 이게 자발적인 프로세스에도 엔트로피가 감소하는 방향으로 그 변화가 일어날 수는 없다. 항상 변화가 일어날 때는 엔트로피가 증가하는 방향으로 일어난다. 네, 그 얘기를 하는 거였고요. 그리고 이 자발적인 반응은 비가역적인 반응을 수반한다. 뭐 이런 얘기가 이 클라우스 이퀄리티 이제 그 핵심 개념이긴 하죠. 그래서 이제 그 예로 이런 힙싱크에 대해서 여러분 설명을 드렸었고요. 결국 요거의 핵심은 그거예요. 그러니까 결국은 어떠한 자발적인 변화가 일어나는 경우에는 그, 그, 그 비가역적인 어떤 그 팽창, 그러니까 비가역적인 반응이 변화가 일어나야 된다. 그러니까 자발적 과정은 무조건, 그러니까 spontaneous change는 무조건 irreversible한 change다 하고 얘기를 해주는 게 이 클라우스 이퀄리티의 의미죠, 사실은. 그러니까 두 가지 의미를 갖고 있어요. 이제 엔트로피가 감소할 수 없다. 일단 그 체인지가 발생할 때, 그리고 자발적으로 스폰테니어스한 체인지가 발생할 때는 무조건 그거는 유니버설한 체인지다 하는 거를 우리가 쭉 이제 설명을 하고 같이 도출을 했던 거죠. 그래서 그 핵심적인 어떠한 그 식들 이런 것들에 대해서 여러분이 그 기억하고 의미를 알 수 있으면 된다 하는 거를 말씀드렸고요. 그리고 이제 이 엔트로피 체인지에 대해서 몇 가지 이제 스페시픽한 케이스에 대해서 떻게 우리가 계산할 수 있는가에 대해서 조금 이제 설명을 드렸었죠. 첫 번째는 아이소서멀 익스펜션인 경우. 요거는 사실 여러 번 다 했던 내용이죠. 이렇게 표현되고 이렇게 표현되고. 그래서 이 내용들 여러분하고 같이 답변 얘기를 했던 거고. 근데 그 요게 여러분이 좀 헷갈리실 수 있었을 것 같아요. 프리 아이소서멀 익스펜션 워크라는 거는 결국 이제 비가역적인 어떤 팽창인데 이거에 왜 비가역적이냐면 이런 거죠. 그러니까 진공 안에서 기체가 이렇게 퍼져나가는 뭐 이런 거라고 보면죠. 그러면 이거는 P 값이 0이 되고 0인 경우 그럴 경우에는 델타 뮤도 0이 되고 그러니까 앞에서 다 했던 내용이에요, 사실. 앞에서 했던 내용들이니까 기억 안 나시면 앞에 한번 다시 보시고 그래서 이게 W 플러스 Q가 0이니까 결국 W가 0이죠. P가 0이니까. 그리고 그러면 Q도 0이고 그러면 외부로 행해지는 엔트로피 변화는 0이고 그래서 토탈 엔트로피 변화는 이렇게만 표현이 된다. 그래서 요거는 볼륨이 익스펜션 하는 방향으로 가기 때문에 항상 요거는 0보다 커지는 거고 그렇기 때문에 요거는 그 비가역적인 반응인 거죠. 여기를 했었고 그리고 페이지 트랜지션 상변태가 일어나는 경우에는 열의 출입이 이 엔탈피 출입하고 동일하기 때문에 왜냐하면 이제 컨스턴트 프레셔고요. 동일한 압력에서 진행되는 반응이고 그래서 우리가 그냥 쉽게 이렇게 표현해 줄 수가 있다. 그래서 우리가 뭐 스탠다드 엔탈피를 알면 엔탈피 값을 알면 트랜지션에서 스탠다드 엔탈피 값을 알면은 그러면 우리가 이런 엔트로피 값도 쉽게 계산을 할 수가 있다 하는 거를 알 수가 있죠. 그리고 온도가 변하는 어떤 그러한 케이스에서는 우리가 어떻게 하느냐. 그래서 간단하게 적분을 할 수가 있었죠. 여기서 알아야 될 게 우리가 이때 컨스탄트 프레셔냐, 반응이 컨스탄트 프레셔냐, 컨스탄트 볼륨이냐에 따라서 이 Q가 CP냐, CV냐 요거를 사용하는 게 달라지는 거고. 그래서 그 값을 사용해서 그러니까 히트 캐패시티 값을 사용해서 우리가 요 값들을 계산을 해준다고 얘기를 하는 거죠. 그래서 이제 요 예제를 풀으시면서 여러분이 스페시픽한 케이스에서 이렇게 계산을 하는구나 하는 거에 대해서는 어느 정도 이해가 되셨을 것 같아요. 그리고 요거는 그냥 여러분 참조로만 보시면 될 것 같고요. 그 엔트로피의 변화량을 어떻게 실험적으로 측정을 하는가 했을 때 그 트랜지션이 발생하는 온도가 변하는 구간에서 어떤 트랜지션이 발생하는 그 시점에서 여러분이 그런 엔트로피 변화를 측정할 수가 있다. 이거는 그냥 여러분이 그거로만 아시면 될 것 같아요. 참조로만. 네, 그래서 오늘 수업은 여기까지 하겠습니다. Okay, so I think we had better stop this class here, and then let's talk again for this thermodynamic concept in the next class. Okay, so thank you for your attention and see you in the next classes.